Math Singer, yum!
I've had plenty of students who believe that solving a given integral first required identifying the integration technique that had to be used. I've even known teachers who gave a list of integrals to their students and asked them to identify each one as an integration by parts integral, or a trig substitution integral, or a partial fractions integral, or whatever. Well, what if I told you that there are many integrals out there that can be evaluated with a whole host of integration techniques? Today, we're going to take a single integral and show how to evaluate it with 3 different integration techniques in 4 different ways. We're going to solve this integral once using trigonometric substitution, again using integration by parts, and then 2 more times with 2 different and unexpected U substitutions. Looking for multiple ways of evaluating integrals takes the emphasis away from the answer and places it squarely where it belongs, on mathematical creativity. Please watch the entire video so that you can decide which of these many solutions most appeals to you. Let's get started. Perhaps the most obvious way to evaluate the integral of x cubed over the square root of 4 plus x squared is by applying a method that is often referred to as trigonometric substitution. In this example, the denominator of the function x cubed over the square root of 4 plus x squared contains an expression of the form constant plus variable squared. Integrals that involve expressions of the form constant plus or minus variable squared, or variable squared plus or minus a constant, can often be evaluated by applying a trigonometric substitution that is suggested by one of the Pythagorean identities. Now, if you're like me, the only Pythagorean identity that you can probably remember with confidence is that sine squared theta plus cosine squared theta is equal to 1. The other Pythagorean identities follow easily from this one by dividing both sides by either sine squared theta or cosine squared theta. In this case, we'll divide both sides of the Pythagorean identity by cosine squared theta to reveal that tangent squared theta plus 1 is equal to secant squared theta. Observe that tangent squared theta plus 1 is also an expression of the form constant plus variable squared. In the case of this identity, the constant is equal to 1. However, the constant in our integrand is a 4. If the x squared in our integrand were equal to 4 tan squared theta, then we could factor 4 out of both terms under the radical and be left with 4 times the quantity tan squared theta plus 1. This seems like a reasonable plan, so we will proceed by wishing that x squared were instead equal to 4 tan squared theta. This is our creative step. We could have chosen to wish for any substitution that we liked in order to change the appearance of our integrand. Everything we do from this point forward is merely a consequence of allowing our wish to be granted. Our first consequence is to notice that x is equal to 2 tan theta. From there, dx is equal to 2 secant squared theta d theta. Incorporating our wish and these 2 consequences into our integral yields quantity 2 tan theta cubed divided by the square root of 4 plus 4 tan squared theta times 2 secant squared theta d theta. Well, 2 tan theta quantity cubed is equal to 8 tan cubed theta. And factoring 4 out of both terms in the denominator and then bringing the 4 outside the radical as a 2 yields 2 times the square root of 1 plus tan squared theta. All of this is being multiplied by 2 secant squared theta d theta. From here, the 2's in the numerator and denominator go away together as a 1, and we can bring the factor of 8 outside the integral. This leaves us with a numerator of tan cubed theta secant squared theta. And the 1 plus tan squared theta in the denominator can be written as secant squared theta, which was the reason for choosing the substitution that we made in the first place. Finally, since the square root of the square of secant theta is just secant theta, we can divide the secant squared theta in our numerator by the secant theta in our denominator and write our new integral as 8 times the integral of tan cubed theta secant theta d theta. We have now successfully written our original integral in terms of x as a brand new integral in terms of theta. It is now our task to see if we can find a way to evaluate our new integral. In order to evaluate 8 times the integral tan cubed theta secant theta d theta, we can begin by writing tan cubed theta as tan squared theta times tan theta. Why would we do this? Well, recalling that 1 plus tan squared theta is equal to secant squared theta, it follows that tan squared theta is equal to secant squared theta minus 1. Therefore, we could replace tan squared theta with secant squared theta minus 1. This gives us a very simple integral in disguise. By letting u equal to secant theta, we see that du is equal to tan theta secant theta. Therefore, our new integral can be written as 8 times the integral of u squared minus 1 du. Of course, this is equal to 8 times the quantity of 1/3 u cubed minus u, plus c. Substituting secant theta back in for u gives us that 8 times the integral tan cubed theta secant theta d theta is equal to 8 times the quantity 1/3 secant cubed theta minus secant theta plus c. Incorporating this result with our earlier work, we now see that we need to find a way to express this answer in terms of x. That is, we need to express our final answer in terms of the variable in which the original question was asked. To do this, let's return to the line that provides the relationship between x and theta. Since x equals 2 tan theta, it follows that x over 2 is equal to tangent theta. Therefore, theta must be equal to the arctangent of x over 2. This means that if we have a right triangle that contains this angle theta, then the tangent of theta must be equal to x over 2. This is because the tangent of the arctangent of x over 2 is just x over 2, since the tangent and arctangent functions are inverses of each other. Well, if the tangent of theta is x over 2, then the opposite side of theta, divided by the adjacent side, must be equal to x over 2. The simplest way to label the side lengths of our triangle so that this is the case is to label the opposite side as x and the adjacent side as 2. It follows from the Pythagorean theorem that the square of the length of the hypotenuse must be 4 plus x squared. In other words, the length of the hypotenuse is the square root of 4 plus x squared. From this, we can see that secant theta, the hypotenuse over the adjacent side, must be the square root of 4 plus x squared all over 2. Substituting this expression in place of secant theta and multiplying through by 8 gives 8/3 times square root 4 plus x squared over 2 quantity cubed minus 8 times square root of 4 plus x squared over 2 plus c. This reduces to 1/3 times the quantity 4 plus x squared to the 3/2 minus 4 times the quantity 4 plus x squared to the 1/2 plus c. We could leave our final answer in this form, or we could choose to go a bit further by factoring out 1/3 times the quantity 4 plus x squared to the 1/2 from both terms. Doing so leaves 4 plus x squared quantity to the 2/2, that is, 4 plus x squared, from the first term, and 4 divided by 1/3, which is equal to 12, from the second term. Therefore, our final answer is 1/3 times the quantity 4 plus x squared to the 1/2 times the quantity x squared minus 8 plus c. In order to evaluate the integral of x cubed over the square root of 4 plus x squared dx, we're going to begin by letting u equal x squared, and then dv is going to equal the rest of the integrand, which is x divided by 4 plus x squared to the 1/2, or x times 4 plus x squared to the negative 1/2 dx. We then have that du is the derivative of x squared, which is 2x dx, and v is going to be an antiderivative of x times 4 plus x squared to the negative 1/2. Well, we can be sure that part of v is going to be equal to 4 plus x squared to the 1/2, so that whenever we differentiate v, we get an expression that involves 4 plus x squared to the negative 1/2. So let's try 4 plus x squared to the 1/2 as a guess and see what happens. Well, if we differentiate that, we get 1/2 times 4 plus x squared to the negative 1/2 times 2x as an answer. Well, the 2 in the 2x goes away together with the 1/2 out front, and we have exactly what we're looking for. In fact, the derivative of 4 plus x squared to the 1/2 power is, in fact, x times the quantity 4 plus x squared to the negative 1/2. We're going to proceed by recalling that the parts formula tells us that our integral is going to equal u times v minus the integral of v times du, and then substitute these expressions in for u, v, and du to give us x squared times the quantity 4 plus x squared to the 1/2 power, that's our u times v, and then we'll subtract from that the integral of v, which is 4 plus x squared to the 1/2, times du, which is 2x dx. Well, what do we have now? So this is equal to x squared times the quantity 4 plus x squared to the 1/2 minus, and now we have to integrate the integral that the parts formula gave us. Well, since it involves a 4 plus x squared to the 1/2 power, we can be pretty sure that 4 plus x squared to the 3/2 power is going to be part of our integral. And if we check this, differentiating, we have 3/2 times 4 plus x squared to the 1/2. Well, there's our 4 plus x squared to the 1/2. And then by the chain rule, we'll have to multiply by 2x. Well, that gives us the 2x that we have in the integral above, but we have that 3/2 out front, which we're going to have to fix up by multiplying by a factor of 2/3. And so that's going to give us the integral we're looking for. An antiderivative of x cubed over the square root of 4 plus x squared is, in fact, the expression that we're looking at right now. We can leave it like that, or we can recognize that both of the terms in our expression involve a 4 plus x squared to the 1/2 power, and so I'm going to factor that out, and for personal preference, I'm also going to factor out a 1/3, and that's going to leave us with, well, let's see, 3x squared from the first term, and then from the second term, we're going to have 2 times the quantity 4 plus x squared. And if we simplify this expression, we have a final answer of 1/3 times the quantity 4 plus x squared to the 1/2 power times, well, let's see, 3x squared minus 2x squared is x squared, and negative 2 times 4 is negative 8. So a final answer, 1/3 times the quantity 4 plus x squared to the 1/2 power times x squared minus 8 plus c. In order to evaluate the integral of x cubed over the square root of 4 plus x squared by u substitution, we can begin by recognizing that 4 plus x squared under the radical would be simplified with a single variable u. So letting u equal 4 plus x squared, du is then 2x dx. And then isolating dx by dividing both sides by 2x gives us that dx is equal to du over 2x. So now we're integrating x cubed over the square root of u times du over 2x. Well, x cubed over x is just x squared, and we can bring the 1/2 out front. So now we're integrating 1/2 times the integral of x squared over the square root of u du. And of course, our integral has to be all in terms of a single variable. So let's go back to our substitution and see that x squared can be isolated as u minus 4. So that brings us to a new integral of 1/2 times the integral of u minus 4 all over u to the 1/2 du, which by dividing u to the 1/2 by each term in the numerator gives us 1/2 times the integral u to the 1/2 minus 4u to the negative 1/2 du. Finally, we are at a position where we can begin actually integrating after having translated our original integral from a question in terms of x into a question in terms of u. Well, this is a relatively simple integral. We'll just write down the 1/2 and then grouping the rest of it, we have 2/3 u to the 3/2 is the integral of u to the 1/2, and the integral of 4u to the negative 1/2 is negative 8u to the 1/2. End the group and add our constant of integration. And we could stop there, but let's go ahead and multiply the 1/2 through both of the terms, giving us 1/3 u to the 3/2 minus 4u to the 1/2 plus c. Now, that looks like a final answer, except our original question was asked in terms of x, and we are at a position where we have an answer in terms of u. So we will go back to our substitution, seeing again that u was equal to 4 plus x squared, and we'll replace all of the u's with 4 plus x squared, giving us 1/3 times the quantity 4 plus x squared raised to the 3/2 minus 4 times 4 plus x squared to the 1/2 plus our constant of integration. And this would be a fine place to end the problem. If we wished, we have in fact found an antiderivative of x cubed over the square root of 4 plus x squared, and it's entirely in terms of x. However, we might recognize that there's a 4 plus x squared to the 1/2 as a factor of both of the terms in our answer. So we can factor 4 plus x squared, actually 4 plus x squared to the 1/2, out, leaving us, well, with the first factor, 1/3 times 4 plus x squared to the 2/2. Of course, 2/2 is just 1. And then we're left with just a minus 4 from the second term. And put in our constant of integration. And simplifying that a bit gives us quantity 4 plus x squared to the 1/2 power times the quantity, multiplying 1/3 through there, gives us 4/3 plus x squared over 3 minus 4, but I'm going to write 4 as 12/3 so that we can see that we can factor a 1/3 out of the second factor, giving us a final answer of 1/3 times the quantity 4 plus x squared to the 1/2 times x squared minus 8 plus our constant of integration. In order to integrate x cubed over the square root of 4 plus x squared dx by u substitution, this time we're going to let u be the entire denominator, 4 plus x squared to the 1/2 power. Well, du then is going to be the derivative of that 1/2 times the quantity 4 plus x squared to the negative 1/2 power times 2x by the chain rule, dx. So isolating dx gives us the square root of 4 plus x squared all divided by x times du. Well, if we go back to our integral, we now have that the integral of x cubed over the square root of 4 plus x squared dx is equal to Well, x cubed over the square root of 4 plus x squared times, and then we'll replace dx with the expression that we found dx to be. That is the square root of 4 plus x squared divided by x du. Conveniently, the square root of 4 plus x squareds go away together, and we're left with x cubed over x. In other words, we've whittled this integral down to x squared du. Well, this leaves us with an integral in terms of two different variables. So we have just a little bit more work to do. But if we just go up to our substitution line where we let u be 4 plus x squared quantity to the 1/2 power, well, taking the square of both sides and subtracting 4 tells us that x squared is equal to u squared minus 4. So we have now transformed our original integral in terms of x into an integral in terms of u that is very easy to evaluate. The integral of u squared minus 4 du, well, that's equal to 1/3 u cubed minus 4u plus c. And if we're not careful, we're going to perhaps erroneously leave this as a final answer. We don't want to do that because the question that we were given was a question in terms of x, and the answer as we have it right now is in terms of u. We want the final answer to be in terms of the same variable in which the question was asked. Easy enough. We know that u is equal to quantity 4 plus x squared to the 1/2 power, so we'll just replace all of our u's with 4 plus x squared to the 1/2 power, leaving us an answer of 1/3 times the quantity 4 plus x squared to the 3/2 power minus 4 times 4 plus x squared to the 1/2 power plus c. This answer is perfectly fine to leave as a final answer, but if we wanted to go just a little bit further, we could recognize that 4 plus x squared to the 1/2 appears as a factor of both of the terms of our answer, and in order to make the final answer just a little bit nicer, we're going to factor out 1/3 times 4 plus x squared to the 1/2 power out of both terms. That leaves us with, well, from the first term, that leaves us with simply 4 plus x squared to the 2/2 power, in other words, 4 plus x squared, minus, well, and then the second term, we're factoring out the entire 4 plus x squared to the 1/2, but then we're also dividing 1/3 into 4, giving us 12. So 4 plus x squared minus 12 is the second factor, and that reduces to 1/3 times the quantity 4 plus x squared to the 1/2 power times x squared minus 8 plus our constant of integration. So, which of these four solutions do you think was the best one? And why did you find it to be the most appealing? Please provide your selection and your reasons in the comments below. Perhaps you can even think of a different solution. Let me know that as well. And if you enjoyed this video, please consider subscribing to this channel by clicking on the link to the right. For now, thank you for watching, and I'll see you in the next video.